Good morning. So, in the previous class, we considered some preliminary results in the theory of differential equations for the first order equations. We also remarked at the end that we will have to look into the issue, namely whether small changes in the statement of the problem leads to small changes in the resulting solution. This is an important issue because at every step of our numerical solution, when we apply these numerical techniques, there will be round off errors which will slightly perturb the problem, and therefore, we are not actually solving the original problem, but we are solving a perturbed problem, which means there are small changes which are incorporated in the statement of the problem, and we are solving the perturbed problem and obtaining a solution. So, we would like to see whether this small perturbation given in the statement of the problem has resulted in small changes in the corresponding solutions of the original problem and the perturbed problem. If that is so, then it is fine. We have absolutely no problem, and we can trust the numerical solution that we have got by using the numerical technique which we have applied to the original problem. If this does not happen, then it is simply not possible to guarantee that the solution that we get represents a realistic solution of the original problem. So, let us define some concepts and then look into results which will guarantee that small changes in the problem results in small changes in the corresponding solutions of the problems. The initial value problem for a first order differential equation is said to be well posed if the following conditions are satisfied, namely the problem initial value problem must have a unique solution y of x, and for any epsilon positive there exists a positive constant k of epsilon such that whenever mod epsilon naught is less than epsilon and delta of x is continuous with mod delta of x less than epsilon on the interval x naught to b, where x naught is an initial point at which the condition is specified, a unique solution z of x to a new problem dz by dx is equal to f of x comma z plus delta of x for x lying between x naught to b with z of x naught equal to y naught plus epsilon naught exists, with the difference between the solution to the new problem, namely z of x, and the solution to the old problem, namely y of x, can be made less than k of epsilon into epsilon for all x naught less than or equal to x less than or equal to b. I hope you have understood the definition. I have considered the original problem. What is the original problem? Dy by dx is equal to f of x comma y, subject to the condition y of x naught equal to y naught, where x lies between x naught and b. I have also considered another problem. What is that problem? dz by dx is equal to, it is the same f of x comma z. It is a new problem because I have an additional term here plus delta of x. This delta of x is the small perturbation which I give to f, so that I have a resulting new problem for the unknown z in the same interval where x lies between x naught and b. In addition, not only the differential equation is perturbed, there is also a change in the initial condition. z at x naught satisfies the condition that it is y naught, which is y at x naught, plus a small increment which is epsilon naught. So, now I have two problems, the original problem and another problem which is a perturbed problem of the original problem, where there is a perturbation delta of x to f and epsilon naught to y naught in the initial condition. So, what does the definition say? The initial value problem, the original problem is well posed. When is it well posed? If the original problem has a unique solution, number 1, that should be satisfied. In addition, the second perturbed problem that we have stated is such that that has a unique solution given by z of x, such that the difference in absolute value between z of x and y of x can be made less than k of epsilon into epsilon for all x naught less than or equal to x less than or equal to b, where this k of epsilon, delta of x, epsilon naught are all given here. So, the second problem that we have defined is essentially called a perturbed problem, which is associated with the original problem. So, the second perturbed problem assumed the possibility of an error delta of x which can be incorporated in the differential equation, and epsilon naught in the initial condition shows that there is a possibility of incorporating a small error in the initial condition. So, the resulting problem is a perturbed problem of the original initial value problem. So, why should we worried about the perturbed problem when we are discussing the numerical methods for solution of obtaining the original initial value problem? The reason is the following, namely, any round off error that is introduced in the representation perturbs the original problem, and therefore, as I remarked earlier, at any step where we apply the numerical method that we are going to develop, we are not solving the original problem, but we are solving a perturbed problem which results due to round off errors. So, we must take care to ensure that the original problem is well posed, namely the definition that we have given earlier is for the original problem to be well posed. So, we check that the original problem is well posed. Otherwise, we cannot guarantee that the numerical solution that we get by solving the perturbed problem will give us a solution which represents realistically the solution of the original problem. So, the conditions that we have given shows that the initial value problem is well posed and are specified in the following theorem. So, let us see what the result is. Suppose we have a set D, which is the set of all x, y such that a less than or equal to x less than or equal to b and y lies between minus infinity and infinity. If f is continuous and it satisfies a Lifshitz condition in the variable y on the set D, then the initial value problem dy by dx is equal to f of x comma y, y of a equal to y naught, where x lies between a and b is well posed. So, we do not have to check by taking a small perturbation to the problem as well as the initial condition and see whether the new perturbed problem has a unique solution and check the condition that mod z of x minus y of x is less than k of epsilon into epsilon and so on. We do not have to do all that. We only have to ensure whether the conditions given in the theorem are satisfied. And the theorem guarantees that if the conditions are satisfied, then the initial value problem is well posed, so that the numerical methods that we develop for such a well posed initial value problem, when they are used to solve such a well posed initial value problem, will yield us solution which are reliable and will be obtained correct to the desired degree of accuracy. So, what are the conditions? F must be continuous and F must satisfy a Lipschitz condition in the second variable y, where on the set D, what is D? D is the set of all x, y such that x lies between a and b and y lies between minus infinity and infinity. This initial value problem is then going to be a well posed initial value problem, so that small changes in the original problem will result in small changes in the solutions that we obtain, so that the solution is a stable solution. So, we now have results which enable us to apply the numerical methods that we are going to develop to initial value problems, so that when we check the conditions that we have given in those theorems are satisfied by the functions f of x comma y in the initial value problems that we consider on appropriate sets, then we are guaranteed that we are solving a well posed problem, and the resulting problem will have a unique solution in an appropriate interval, so that our numerical solutions that we obtain are reliable solutions obtained correct to the desired degree of accuracy. So, let us take an example and complete this discussion. So, let D be the set of all x, y such that x lies between 0 and 1 and y lies between minus infinity and infinity. Let us consider the initial value problem given by dy by dx is equal to y minus x square plus 1 for x lying between 0 and 2, y of 0 is equal to 0.5. So, let us find what is modulus of fy. So, it is modulus of d by dy of f, which is y minus x square plus 1, and that will give you 1. So, f of x comma y therefore satisfies a Lipschitz condition. Why? Because we have been able to find out capital L, which is 1, which is true valid for all x, y in that set D, and therefore we have f of x comma y to satisfy a Lipschitz condition in the second variable y on the set D with Lipschitz constant L is equal to 1. In addition, the function f is a continuous function on D, and therefore, by the theorem that we have considered, the initial value problem is well posed, right. So, we now verify whatever we have said directly. So, what do we have to do? We should consider a perturbed problem. This is not necessary, because we have already said that the original problem is a well posed problem. However, we would like to start with a perturbed problem and then show that the original problem is a well posed problem. So, let us consider a perturbed problem, which is dz by dx, which is equal to the same f as a function of x and z. I give a small perturbation, say delta, to the right hand side, and z of 0 initial condition is y of 0, which is 0.5. I give a small perturbation, say epsilon naught, to the initial condition. So, delta and epsilon naught are some constant. So, when is it well posed? Condition 1. The original problem has a unique solution. So, let us solve dy by dx is equal to y minus x square plus 1, y of 0 equal to 0.5. It is clear that this equation is again a linear Lagrange equation subject to this initial condition, and therefore, it has a solution which is given by this. One can also directly verify by differentiating it and showing that you obtain this differential equation. So, the first condition is satisfied, namely the original problem has a unique solution in this interval. Now, let us consider a perturbed problem. We should show that the perturbed problem also has a unique solution given by z of x. So, the perturbed problem has right hand side z minus x square plus 1 plus delta with z of 0 given by 0.5 plus epsilon naught. So, again it is a linear Lagrange problem with initial condition. When you solve, you get z of x to be equal to this. So, if mod delta is less than epsilon, so delta is an increment given to the right hand side, it is a perturbation given to the statement of the problem. So, if you take mod delta to be less than epsilon as well as mod epsilon naught to be less than epsilon and find out the difference in the solutions of the original problem and the perturbed problem, then it gives you modulus of delta plus epsilon naught into e power x minus delta, which is nothing but modulus of delta plus epsilon naught into e square, because our x is less than or equal to 2, plus mod delta. So, this is less than or equal to twice epsilon into e square, because mod delta is taken to be less than epsilon, mod epsilon naught is less than epsilon. So, 2 epsilon e square plus epsilon, which is 2 e square plus 1 into epsilon. Recall, we should be able to find out k of epsilon. Let us look at the second condition that we have given for a problem to be well posed. The second condition says that for any epsilon greater than 0, there exists a positive constant k of epsilon such that whenever mod epsilon naught less than epsilon and mod delta less than epsilon on this interval x naught to be, a unique solution z of x to the perturbed problem exists. Yes, we have shown that. And modulus of z minus y must be less than k of epsilon into epsilon for all x naught less than or equal to x less than or equal to b. So, you should be able to find this k of epsilon. Yes, in the example that we have considered, we have been able to show that mod y of x minus z of x is less than or equal to 2e square plus 1 multiplied by epsilon. So, this 2e square plus 1 is the k of epsilon that we are looking for, and this is so for all x, and therefore, the problem that we have considered is such that the original initial value problem has a unique solution in that interval, and we have been able to find out a k of epsilon such that the absolute difference between y and z can be made less than k of epsilon into epsilon for all x in that interval. So, both the conditions are satisfied, and therefore, by the definition of a well posed problem, the problem that we have considered is a well posed problem. So, we actually have demonstrated how one can find that k of epsilon and show that the two conditions given in the definition are verified, so that the original problem is a well posed problem. We also have shown earlier that the conditions specified in the theorem are satisfied, and therefore, it is a well posed problem. In both ways, we have been able to establish the well posed property of the corresponding initial value problem that we have considered. So far we have looked into the important results which are required so that we can move further to develop numerical methods that will guarantee that they are reliable. So, we now have a knowledge of what are all the factors that we should keep in mind, so that we have a reliable solution obtained using the numerical techniques that we have developed. So, we are going to now develop a number of numerical techniques with the help of which we can solve an initial value problem governed by the first order differential equation. To begin with, we are going to consider methods which are called single step methods, which are also referred to as explicit methods. You will understand the meaning of what a single step method is, why is it an explicit method when we develop these methods. A very powerful method which is a single step method that is used in obtaining solution of a first order differential equation is Taylor series method. So, let us see what this method is. So, in a Taylor series method, our goal is to solve an initial value problem dy by dx is equal to f of x comma y, subject to the condition that y of x naught is y naught. As we already remarked, we are trying to get a numerical solution of this differential equation. So, we are going to construct a table of function values of the form x naught, y naught, x1, y1, etc., xn, yn, where yi represents the computed approximate value of y of xi, where y of xi is the exact solution of the initial value problem at any xi. So, as we said already, once we know the table of values, we can reconstruct this function y is equal to y of x. So, Taylor series method requires the following assumption, namely we assume that various order partial derivatives of f of x comma y exist. So, let us consider the initial value problem. So, if I start at any x and if I want to find out the solution at say x plus h, then I use a Taylor series expansion of y, so that y of x plus h is y of x plus h y dashed of x plus h square by factorial 2 y double dashed of x plus h cube by factorial 3 y triple dashed of x plus h power 4 by factorial 4 fourth derivative of x, first derivative of y at x plus etc. Suppose say in this expansion we decide to take only terms including h to the power of 4 by 4 factorial into fourth derivative of y. Then the terms that we have neglected start from h power 5 onwards, and these are the terms which contribute to what is called the truncation error that is inherent in our problem. What is a truncation error? The truncation error is an error due to truncating an infinite process to a finite process. So, in this case we have a Taylor expansion of y of x plus h which contains infinite terms, but we truncate it say at the term which contains h to the power of 4 by factorial 4 into fourth derivative. So, an infinite process is truncated and only a finite number of terms is taken into consideration. When this is done, we come across what is known as truncation error, and because of what we are doing, this truncation error is inherent in our procedure itself, and it is independent of the round off error that may occur. So, the resulting numerical method that we have after truncating say at terms h to the power of 4 by factorial 4 into the fourth derivative of y, it is called the Taylor series method of order 4. So, it includes in the Taylor series terms up to h to the power of 4 and terms of order of h to the power of 5 and higher orders are neglected. Then we have Taylor series method of order 4. So, we give the definition. The order of the Taylor series method is said to be n if terms up to and including h power n by n factorial into nth derivative of y are used in the computations. So, we observe that at each step we have local truncation error. What is it? It is of order of h to the power of 5, because we are omitting terms of order of h power 5, h power 6, etc. The first neglected term is of order of h to the power of 5. So, the local error behaves like a constant times h to the power of 5 as h goes to 0. And so, if h is taken to be say 0.01, that is h is taken to be 10 to the minus 2, then h power 5 is 10 to the minus 10. So, you may think that the error that is incurred, namely that local truncation error, is of the order of 10 to the power of minus 10 at any step, which is very, very small, which can be neglected because it is of order of magnitude 10 to the power of minus 10 at any step. But these small errors get accumulated as we move on from one step to another step, and there is a considerable amount of error that is incorporated during the computation of the solution. So, the question is, can you estimate this local truncation error at each step of your numerical computation? Yes, it is possible. So, let us see what is the estimate. So, we know that the error term in the Taylor series of order n is of the form, say E n, which is equal to the first neglected term. What is it? We have included terms up to h to the power of n in our computation. The first neglected term is 1 by n plus 1 factorial h power n plus 1 into n plus 1th derivative of y evaluated at x plus theta h, where theta lies between 0 and 1. So, this is the local truncation error when we use Taylor series method of order n in computing the solution, where at x plus h, when we have information about y at x. So, can you give an estimate? Answer is yes. What do? We write down, approximate this n plus 1th derivative of y at x plus theta h in terms of the finite difference. Namely, E n will be 1 by n plus 1 factorial h power n plus 1 into the n plus 1th derivative is replaced by a forward difference approximation, namely it is the nth derivative at x plus h minus the nth derivative at x divided by h. Clear? So, that will be equal to h power n by n plus 1 factorial multiplied by the difference in the nth derivative of the function at x plus h and x. So, this is done after estimating the n plus 1th derivative of y at x plus theta h. So, we have an estimate of this error when we use Taylor series method of order n. So, we observe that E n is h power n by n plus 1 factorial multiplied by some quantity. This is the estimate of the local truncation error. So, we now have to see, is this the only error that we come across during our computations? No, we have different types of errors which we come across as we move on with the numerical solution of the initial value problem. The first type of error is what we have seen, namely the local truncation error. What is it? It is the error that is made in one step when we replace an infinite process by means of a finite process. So, as we have remarked, this truncation error is present at each step of our computation. It is inherent in the method itself. And note that in Taylor series method, this is what we do. We replace an infinite Taylor series for y of x plus h by a finite sum of terms, namely by a partial sum. And it is independent of the round off error, and the local truncation error is said to be of order h power n plus 1 when we retain terms up to and including h power n in the series. This is the first type of error that we come across when we apply this Taylor series method to solve our initial value problem. Another type of error is what is called the round off error. Why does it occur? It occurs because of the limited precision of the computer that we have. So, the magnitude of the round off error depends on the word length of the computer that we use, or it depends on the number of bits in the mantissa of the floating point machine numbers. So, it occurs due to the machine that we use to compute the numerical solution. Then the third type of error that occurs is global truncation error. Why does it arise? So, we said that the local truncation error occurs at each step of our computation. So, the accumulation of all these local truncation errors yields the global truncation error. So, even if you perform your computations using exact arithmetic, right, this global truncation error will be present in your numerical solution because it occurs due to the accumulation of the local truncation error. And again, this global truncation error is independent of the computer that you use to obtain a numerical solution. So, where do you start your computation? You start your computation at some initial point x naught. Why? You want your solution curve to pass through the point x naught comma y naught. So, you start your computation at this point because your curve passes through this point y of x naught equal to y naught, and now you move to the next point which is x naught plus h. Alright. So, you have moved to one step, and at this step you have a local truncation error. Suppose say you are interested in getting the solution to this initial value problem in an interval of the form x naught to some b. So, you will divide this interval x naught to b into a number of subintervals. So, let us see how we do it. So, we will divide the interval x naught to b into a number of smaller subintervals of the form b minus x naught by n equal to h. So, that x1 will be equal to x naught plus h, x2 is x naught plus 2h, and so on. Xi is x naught plus ih. So, you will use your Taylor's method and compute what is y of x1, that is y of x naught plus h, which will be involving some finite number of terms, and you omit this term which contributes to the local truncation error. So, you arrive at its value. So, now you have y at x1 to be say some y1 using this method. Now, you use this information and move to this point x2, which is which is the next point. So, you compute y at x2 here. Again, what will you do? You will say y of x2 is y of x1 plus h. You employ Taylor series, truncate it up to a finite number of terms, say up to terms involving h power n. You have omitted this term, that will contribute to the local truncation error at this step. Clear? So, every time you move ahead by one step till you reach the point B, at which you will determine your solution using Taylor series method. So, number of steps necessary to reach that point B is going to be, if I call it xn, B is what I have called as xn. Please look at the monitor. Then the number of steps necessary to reach this point xn, which is B, is xn minus x naught by h. You have moved so many steps. The number of steps is given by xn minus x naught by h. So, if the local truncation error at each step is of order of h power n plus 1, why? You have used a Taylor series method of order n by retaining terms up to h to the power of n. So, your local truncation error is of order of h power n plus 1, and number of steps to reach this point xn is xn minus x naught by h, and at each step you have accumulated the local truncation error, and therefore, what is the global truncation error? It is going to be proportional to 1 by h into order of h power n plus 1, namely it is going to be of order of h power n. So, if the local truncation error in Taylor series method is of order of h to the power of n plus 1, then the global truncation error is of order of h to the power of n. So, if the global truncation error of a method is order of h power n, then the numerical method is said to be of order n. Then what about the global round off error? Yes, what is it? It is the accumulation of the local round off error in the previous steps. And then what is the total error? The total error is the sum of the global round off error and the global truncation error. So, as I already have said, if the global error is of order of h power n, then we say that the numerical procedure is of order n. So, we now know what we mean by Taylor series method of order n, right, which we want to apply to an initial value problem and see how the solution can be obtained. So, let us consider the initial value problem. Dy by dx is equal to f of x comma y, a less than or equal to x less than or equal to b is the interval in which I want to get the solution. Condition is y of a equal to y naught. So, suppose the solution to the problem has n plus 1 continuous derivatives, that is y can be differentiated n plus 1 times, the derivatives exist and they are also continuous. Then I expand using Taylor series, right, y of xi plus 1, which is y of xi plus h, that is y of xi plus h, y dashed of xi, and so on. For the last term which I want to neglect, which is the local truncation error, is h power n plus 1 by factorial n plus 1 into n plus 1th derivative at psi I, where psi I belongs to xi plus 1. So, I compute the derivatives which appear there as terms of the Taylor series, namely y prime, y double prime, etc. Y prime is f of x y. What is y double prime? It is d by dx of y prime. But what is d by dx of y prime? So, let us see what it is. So, y prime is f of x comma y. So, I require y double prime, which is d by dx of f of x comma y. What is d by dx of f of x comma y? It is d by dx of a function of two variables x and y, where y itself is a function of x. So, it is nothing but the partial derivative of f with respect to the first argument plus the partial derivative of f with respect to the second argument into y with respect to x. So, this is fx plus fy into what is y prime? It is f. So, you have got your second derivative as fx plus ffy. So, let us compute the third derivative. So, it is d by dx of fx plus f into fy. So, we have a function of two variables here, and I require d by dx of that function of two variables. So, it must be equal to, take this first term. So, the derivative of the first term with respect to the first argument x plus derivative of the first term with respect to the second argument, namely y, into y with respect to x. So, we have obtained d by dx of this. We now move on to d by dx of this term. We see that it is a product of f and fy. So, we must apply the product rule while taking the derivative. So, it is going to be f into d by dx of fy, that is the first term, plus the second term is fy into d by dx of f. So, this will be fxx plus fxy into what is y prime? F. Again f into, I require d by dx of fy, but fy is a function of x and y. So, it is a function of two variables. So, it must be fy with respect to first argument plus fy with respect to the second argument into y with respect to x, that is y prime, which is f itself. Then I go to the next term fy into d by dx of f, it is a function of two variables. So, f with respect to the first argument plus f with respect to the second argument into y with respect to x, which is f itself. And so, the third derivative of y is fxx plus, you observe that you have a fxy and you have a into f and you have a f into fyx. Function f is a continuous function, and so the mixed partial derivatives are equal. So, we have f into fxy plus f into fyx to contribute to twice f into fxy. Then the next term is f square into fyy, and then we have fx into fy, then we have f into fy square. So, this is our third derivative y triple prime. Similarly, the higher order derivatives can be computed, and they involve the partial derivatives of various orders, and these have to be evaluated where at xi and then substituted on the right hand side in the Taylor series expansion, and then the value of y at xi plus 1 must be obtained. So, if I use a Taylor series method of order n, then how do I get it? Y at a is y naught and y I plus 1. What is the notation that I use? If I compute y of xi plus 1, namely y at xi plus 1, then when I use a Taylor expansion or Taylor series method of order n, I obtain an approximate solution. I shall denote that solution by y I plus 1. So, that is the notation that we have used here. So, y I plus 1 will be y I plus h y dash I plus etc. up to h power n by factorial n into nth derivative of y evaluated at xi. I have neglected the higher order terms. The first neglected term is of order of h to the power of n plus 1. So, the local truncation error that is incurred by using a Taylor's method of order n is order of h to the power of n plus 1. So, we thus have understood what Taylor series method of order n is and what are the conditions that have to be satisfied by the function f in order that we have a reliable numerical solution. Say at points which are given by x1, x2, etc., say xn. So, we can move ahead from one step to another step using the information available to us at the previous step and compute the solution at this step. Namely, if I have information at x naught which is given by the initial condition, I use Taylor series method of order n, get the solution at x1. Now that I have the solution at x1, namely y1, I solve a new initial value problem. What is it? Dy by dx is f of x comma y subject to the initial condition y of x1 is y1. So, I can get the solution at the next point, namely what is y at x2, again by Taylor series method of order n. So, I get y at x2 which is y2. So, I move every time by going over to the next point which is in steps of h, where xi is x naught plus ih, and reach the end point of the interval where I require the numerical solution. So, I now have solution at a set of discrete points x naught, x1, x2, etc., xn, which are denoted by y naught, y1, y2, etc., yn. So, we have the solution at a set of discrete specified equally spaced points, and this is what we want. This is what we call as the numerical solution of an initial value problem. So, we now have learnt Taylor series method of order n by means of which we can solve an initial value problem. So, in the next class we shall take up some examples to illustrate this method and then see the range of values of x for which such an approximation will be a valid one. So, we will continue in the next class.